You stand before this court, condemned of the most vile crime, of attempting to assassinate our Dark Lord.
Death! Throw him in the pit! Death! Shame!
Silence in court! This crime is so despicable that death itself is too good for you. You are to be condemned to a fate worse than death. You are to be taken deep into the recesses of our Dark Lord, his mountain, and put into an old orc dungeon, where even his mightiest servants fear to tread. Guards, take him away.
"3D Maze" from Graphic Adventures for the Spectrum 48K. There are no user-defined graphics in this program, as the high-resolution plot and draw commands have been used. The main section of the game has been written entirely in machine code, which makes for a much faster game. The machine code being a series of numbers, which must be entered into high memory using the loader program. First of all, you must make sure that caps lock is engaged and then type in the basic program 3D Maze. Special care must be taken when entering the USR number, as a wrong number may cause a glitch or system restart. Once entered, the program must be saved using the command save 3D Maze line 10. This program should be saved on tape and verified using verify. At this stage, you should make sure that the tape remains in the same place, or the position on the tape counter is noted so that another section of data can be saved directly after it. Now, type in the decimal loader program again, checking that caps lock is engaged. Once complete, it should be run. An address should appear on the screen, which is one of the numbers in the decimal dump. You must enter these numbers one at a time, a new address being printed on the screen at the end of each line, just as in the dump. At the end of each section, the computer carries out a simple error checking routine. If any errors are discovered, it will allow you to check the numbers you've just entered against those in the decimal dump. The section is printed line by line, and Enter allows you to move on, while C allows for a line to be corrected. This will continue until the computer finds no more errors. Great care must be taken when entering the numbers, because the computer does not find all errors, and one wrong number could cause a glitch when the game is played. You now have to save the data in 4 sections just after the first program, 3D Maze. When the tape is ready, press Enter to save the first block of data. This must be repeated 3 more times, after which all 3 sections should be verified. The game is now complete. Type Load 3D Maze and everything will then load automatically. So, you saw it loading multiple bits of machine code. There are a number of things to note. It runs really fast. To be fair to the game, it is very, very fast. You had a very similar maze-type experience in the previous game in the book called Dragon, and that was a bit slow. This game is very fast. It also lets you change the maze. So you have to put the maze data is stored starting at address 41,000, and that's one of the bits of machine code you have to load. 0 is a space, 1 is a wall, and 2 is the exit. However, you then need to poke various bits of machine code as follows. Poke 6141x plus 2, with x being the size of the maze, and there are actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pokes. Oh, and then 11, 12 pokes, and then 13, 14 different pokes you've got to put in. So although it does work, it's a little bit fiddly. The maze must be a square. The maze must be surrounded by walls. Corridors must all be of unit width, which means you can't have half units, because that doesn't make any sense. But also you can't have any wide rooms, because the program doesn't display those very well, unfortunately. You've got to include a start position and the exit. How the exit is coded in 2 different ways, one of which will display a sign saying this is the exit, The other one actually notices when you want the game. In order to play the game, the book says you use the Sinclair Interface 2 joystick. 6 is left, 7 is right, 8 is forward. In fact, those keys don't work. There's the exit there. It's 7 is right, 7 is left, 8 is right, and 9 is forward. And that is us winning. So, I think there's room for improvement here. I think we could make our own maze, but with blackjack and hookers. So, let's make it better. The game is designed so that the maze can be changed by the user. However, great care must be taken to ensure that the machine code routines operate correctly. It doesn't help that the figure in the book has the incorrect address. Design a maze similar to that shown in the book, which is a nice square, making sure to obey the following rules. The maze must be a square. The maze must be surrounded by walls. Corridors must all be of unit width. You must include the start position and the exit position. Then you poke the machine code variables, which are either set to x, which is the width, x plus 2 or 2 times x minus 1. The maximum size of maze you can use is 94. Otherwise you run into the other machine code routines. Once you do that, you start poking the maze into memory, starting at location 41,000 and setting the fields to be either 0 for a space, 1 for a wall, or 2 for an exit. You then do some more pokes. So what I've done here is made up a little editor. This does limit you to a maze of 20 by 20. It starts off, it sets the walls for you. You then move your cursor around using the cursor keys. You put S for the start, X for the exit, and then you press 0, which sets a wall or turns a wall off. You can also then press A, B, C, D, E, and F, which I'm putting in for expansion purposes to make the maze a little bit more interesting. So when you come to save the game, S is not marked at all within the maze. The exit is marked with the 2. A is marked with 4. B with 8. C with 16. D with 32. E with 64. And F with 128. These are individual bit settings. But as you can see here, all I'm doing is filling in the walls. The flashing cursor is done by printing the asterisk, then a space, then what was on the square before, then another space. So when it's on top of a wall, you'll see the asterisk flashing and then the wall, or the letter S and so on. Because underneath this is a one-dimensional array, and I then use the size to determine which row you're on as well. So this editor does not check that your corridors are 1 unit wide. If you do break that rule, it still works, but you get ghost walls. It had exactly the same problem in Dragon. Unfortunately, in Dragon, he did have wide corridors at certain points, which made mapping quite difficult. You thought there were walls and doors, but there weren't really. So here we're continuing to place walls around the maze. We've got our start in the top left, exit is bottom right, 6 different points of interest. Once you're happy with the production, you press letter T, and it will then go and verify to make sure everything's correct. So make sure that you have a start and you have an exit, and only one start and only one exit. Once that's done, it will then populate the memory with all the bits and the bytes, and then you get to save it to tape. And having done that, it'll give you a screen full of pokes you need to put in, and then you're best to copy that and then type them in. 3, 2, 1, and action. So the game as written is black and white, which is a bit of a shame because the ZX Spectrum is known for its panoply of colours. 15 are available. So as a first simple change to a mainly machine code program, we can change the code in BASIC. So the line that changes the colour is line 220. Line 220 sets ink to black and paper to white and then clears the screen. I'm going to go with red ink and not black paper but blue paper. So I get red ink on blue. And it doesn't quite work. We get a blue background mostly, but anywhere the walls are involved, we get horrible colour clash. And it's because the machine code clears the screen, the entire screen, and it gets some of the data from the 2 lines for input, and it gets those by default from the border. So if we put a border of 1 in instead, we get a nice blue border, and then try again, it should work a lot better. And it does. However, we get white ink, but a blue screen, which is a lot prettier. So we've changed the colours. We've created an editor to make creating mazes easier. Now to make some change to the game itself. The game is written entirely
apart from the very simple string generation at the start and the end, in machine code. A list of numbers. Lots and lots of numbers. There are numbers which represent the string exit. There are numbers that represent the maze. There are 4 pages representing the maze. And there are 1, 2, 3, 4, 5 pages representing data, which is something to do with producing the 3D image, which is very fast, and I don't know what they do. If you take bits out, they don't work. If you take all of it out, nothing works. So they're very mysterious, and I can't work out what they do. And then there are 3 pages or so, which is the chart in the background, and is the start of it, of the game itself. These are displayed as numbers. So how do you know what they do? Well, if you've seen my earlier video on the Usborne Introduction to Machine Code, you get an idea of what you have to do with these numbers. You poke them into memory, then you execute them. What do the numbers do? If you go to the back of the Spectrum manual, you will find a full list of what they all do. Here we are. Here's a list of the Spectrum character set and the Z80 assembler. For example, 0 is not no instruction. That's fine. Then you get certain codes like hex CB, which is a special instruction. Also, there's a compound instruction. That is a bit instruction. So, for example, hex CB followed by hex 56 is the instruction bit 2 brackets HL. What that means is it looks at the second bit, starting, it says bit 0, bit 1, bit 2. Third bit, the bit is either 4 or 0. If it's set, then we set a flag, the N flag, I believe, to on. And then you can say, if 0, do something else. That is not listed in here. This is just what the mnemonics are. So you then might need to look at an introduction to Z80 machine code, which actually explains what on earth goes on. If you're a bit more hardcore, there's Rodney Zax's Programming the Z80, the standard reference guide. But then you may also find, and you will find in this particular program, you're going to want this as well, the Spectrum ROM disassembly, because we make several calls to bits of the ROM in order to clear the screen, in order to do the plot and to draw. And without knowing what they do, you won't have a clue what's happening. So, let's have a look at my adventures.
One of the things I noticed playing the game was it wasn't very exciting because the maze was, well, frankly, rather dull. So we're going to add some extra terrain features into the maze, just of interest. The bit of code that detects and then calls the bit of code that displays the exit sign is at address 60378. I know this because I disassembled that bit of code, which produced 15 pages of a Word document working out what's going on. So we're going to show what these 7 bytes are that detect the exit. 203, 78, 40, 3, 205, 101, 236. So the first 2 bytes are a pair, which is the bit instruction, which means the next instruction goes on and looks up in the bit table, which is a different table. So this is look at bit 1, which is the second bit, at whatever HL is currently pointing at. So bit 1 is actually the bit that says is it 0 or is it 2? And it sets the Z flag accordingly. So if it's 0, it's 0. If it's set, then Z is not set. Next, we look at 40 and 3. These are decimal numbers, which is jump relative on 0, 3. So if the second bit is not set, so it is not 2, jump forward 3 from the next instruction. So the next instruction is 3 bytes long, which is 205, 101, 236. So we're going to jump forward. So it's actually potentially a little if statement. And then 205 is the call XX instruction, which means call the address in the 2 bytes following it. The address is a 2-byte pair. The first byte is the low order byte. The second byte is the high order byte, which is that value times 256. So that bit of code calls the section that does the actual printing of the word exit. So remember that whenever you see an address in Z80 code, it's always low order byte first, not the other way round, which So if you're using calculators to work them out, it can get a bit confusing. So this works out as 236 times 256 plus 101, which is 6517. So we know we need to move the code. Each character we wish to be sensitive to is going to require 7 bytes. There's 7 bytes of the data on see on the screen, and the only thing that will change will be the address they call and which bit we're sensitive to. So we're going to need to shift all the subsequent code down by 7 bytes per character. We're looking at bits 4, 8, 16, 32, 64, 128. That's going to be by 42. So we're starting at 6385 is then bit immediately after the exit detection, and we're then shifting everything down by 7 bytes. Times 6 for 6 characters. I'll do this with a good old poke. So see here, I've just done a poke here. This is the first time I've done it, just to make it work. No problems you can see here. Everything's copied down fine. Everything should just work. So let's give it a go. The game starts, 3D maze, skip to the intro, off we go, into machine code. Oh dear, it didn't work. Let's find out why. So there are lots of ways of moving around machine code. You can have relative calls, which you've seen with jump relative on 0.3, but you can also have hard-coded calls such as call itself and jump. Because call is go and come back, jump is just go there and do not come back. So we need to work out where they are and change the ones that have now moved because they're now wrong. So what we're going to do is use a bit of peeking to investigate where in the machine code we have calls, and then that'll give us a bit of a clue as to what we need to change to fix things. So the call instruction is decimal 205. That's the first one we're going to look at. So that's our bit of instruction. We've got a little bit of a for loop. Unfortunately, I started at 6385. We should start at the start of the machine code in case there are some sneaky calls until later, which there are. However, the basic procedure is fine. So just to say, if the thing we're looking at is 205, it's probably a call statement. It may not be, but it might be. Then put call question mark and say what the address is, so we have a clue what's going on. So let's give that a go. And we have a rather large number of calls. However, we don't have to worry about all of them. We're going to focus on one address at a time. If the call is to the ROM, well, we've not changed the ROM. If the call is to somewhere in our machine code that's before the move, before 6385, again, we don't need to worry. So we're going to refine our for loop to get a better idea and going to look for the specific address. So 205 is call. So we're going, if it's 205, and then the next byte, which is peak brackets I plus 1, you want to do the in brackets, otherwise you'll get peak I, then not add 1 to it. So we can look at the address we're particularly interested in, with the low order byte is first, then the high order byte. I'm calculating these using a calculator. So we're looking for address 6502, which is now moved. So now this will only tell us the calls in question. And we've got 7 of them, which is what we'd expect. 7 characters we're interested in. So now we need to go and fix those. So this is the machine code to do a print using the Spectrum ROM. So the first thing we do is open channel 2 with a call 1601 with 2 in the accumulator register. That takes up the first 5 bytes. We then load the register pair DE with the value 40,500. This is some of the code that we loaded from memory. We then load register pair BC with 19, which is hexadecimal 13. That is the string to print the exit sign. Why is exit 19 characters long? Because it starts off with a control character for @ then the row and the column data, and then for every character we have flash is on and also inverse, so it's much longer than you think. Having set all that up, we call the print routine and then print our character. We need to duplicate this for our other 6 characters, and then we can play. So this is the result after more hours than you'd think for the results we get. So I've loaded up the game, I've replaced the bits of machine code, I've added extra string data, we support that now, we've changed the colour, I've also corrected the key so it will now work properly with a singular joystick. So 6 is left, 7 is right and 9 is forward. So it still works nice and fast. You can see a long way down the corridor, which is very technically impressive. Oh look, a sign saying blackjack. It's a string floating in midair, not very long, it would be better if it was shorter, but certainly there. Once you get close enough to it, on the square is actually on, it's gone, but if you turn back, it's still there. So keep going around the corner, our blaze, there it is, blackjack. So keep moving around the maze. I put those strings in just to make it a bit more interesting, otherwise you get nothing. Oh, we have blackjack and hookers. The maze is already better. This is the maze I made myself, 17 by 17 with the outer walls. Again, you could have a maze which is 94 by 94. Imagine how tedious that would be. So we move around the maze, nice long corridors. There are 6 points of interest. You don't need to visit them all. I am because I want to show you these strings, which you have to encode in memory. Change the print routine that you've copied to point at the different strings and make sure you get the length right, otherwise you get strange values. Because if you print null, which is low values, you get strange characters. Here you have hopeless, we have despair. So I thought it's suitably gloomy messages for this maze where the Dark Lord's minions fear to tread. So move around this maze. Where should we go? Let's go down this way. As there is no compass in game. Things I could have added is changing the border by use of the out254 command as a give up statement. That also have the opportunity of adding footstep sounds. Because if you write 16 to out254 and then a different number, you get two sort of clicky sounds, one of which louder than the other. I think one is the ear and one is the mic. I'm not sure which one is which. But on my experimentation, it was reasonably as a tick, took, tick, took, tick, took sort of sound. So that would have been quite interesting. However, to put it in, I would need to remove all the code down again and then recalculate all the jumps and calls. Here's the exit. Remember, 19 characters long to get that exit effect. And here we are. This is the end of the game. So now we shall move on to final thoughts. Of the games in the book so far, this has been my least favourite. It's very technically accomplished. However, you learn nothing by typing it in. There's huge amounts of typing in to do. And the maze itself, although technically interesting, is rather dull to navigate. Computer Video Games magazine said the book was okay, but couldn't comment on the suitability of the programs because they didn't actually go around to typing them in. However, Micro Adventurer did, and they had a different opinion to me. So on the face of it, they thought the games were mediocre. However, in purely programming terms, the only interest in the 7 games is the machine code routine given for the fast generation of a 3D line-drawn maze, which they really, really liked. I think it's very well done, but it's not very portable to anything else. You can't learn unless you have lots of books and time, like me, so it's not really useful. Thank you for watching.